In 1971, a mathematician at Bell Laboratories calculated a number so large that if you tried to hold it in your head, the information density inside your skull would exceed a hard limit of physics, and your head would collapse into a black hole. That is not a metaphor. That is not a thought experiment designed to make a point. That is what the equations of general relativity and quantum information theory produce when you ask them how much data a region of space the size of a human brain can contain. The answer is approximately 3.6 times 10 to the 42nd power bits. And the number that Ronald Graham calculated as an answer to a genuine, published question in combinatorics requires so many digits that the number of digits and the number of digits of the number of digits and the number of digits of that, continuing this recursion for more layers than there are particles in the observable universe, still does not get you to a description of how many digits Graham's number has. The number is physically dangerous to store, and it is the answer to a real question. And it exists right now with exact, provable properties in a mathematical landscape that the entire physical universe is too small to contain. That is the fact. Here is the part nobody tells you. We know the last 500 digits of this number. We know them with absolute mathematical certainty. The last digit is 7. The last 10 digits are 2, 4, 6, 4, 1, 9, 5, 3, 8, 7. These are not approximations. They are exact. We can prove rigorous, deterministic theorems about the properties of an object that cannot physically exist anywhere in the observable universe, not in your brain, not in every brain that has ever lived combined, not in a computer the size of the Milky Way, not in a hypothetical computer the size of the entire observable universe operating since the Big Bang. If mathematics were just a language we invented, a bookkeeping tool, a useful fiction, this should be impossible. You cannot have exact knowledge about a fictional object that transcends physical reality. You do not get to say this number is odd, and this number is divisible by 3, and this number ends in 7, about something that is just a squiggle on a page. Either those statements are true, in which case a number exists independently of any page or brain or universe to write it in, or they are not true, in which case the entirety of mathematics collapses, because every proof that depends on the properties of large numbers, which is virtually every proof in modern mathematics, becomes unreliable. The number does not need the universe in order to be true. That should bother you more than the black hole part. And the actual relationship between mathematics and the physical universe is the opposite of what you were told. Not math inside the universe inside math. And the people who understand this best, the physicists and logicians who have been circling this implication for 60 years, have known it for decades. They just never figured out how to say it without sounding like they had lost their minds. I want to show you why. The problem that produced Graham's number starts innocently enough, the way the worst problems always do. Imagine a cube. Not a 3-dimensional cube, that is too simple, but an n-dimensional hypercube. A square is a 2-dimensional hypercube with 4 vertices. A regular cube is a 3-dimensional hypercube with 8 vertices. A 4-dimensional hypercube, called a tesseract, has 16 vertices. Each time you add a dimension, the number of vertices doubles. An n-dimensional hypercube has 2 to the n vertices. Now connect every possible pair of vertices with a line. This creates what mathematicians call a complete graph on 2 to the n vertices. In a regular three-dimensional cube, that is 28 edges. In 4 dimensions, it is 120. The numbers get large fast, but they are still manageable. Now color every single one of those edges either red or blue, any coloring you want. Random, systematic, adversarial, it does not matter. The question Graham needed to answer was this: how many dimensions does the hypercube need to have before every possible 2 coloring of its edges is forced to contain a monochromatic, complete subgraph on 4 coplanar vertices? Meaning, no matter how cleverly you color the edges, no matter how hard you try to avoid it, somewhere in that hypercube, there must exist 4 vertices that all lie in the same 2-dimensional plane and whose 6 connecting edges are all the same color. This is a question in Ramsey theory, the branch of mathematics that proves certain patterns must exist in sufficiently large structures. Not might exist, not probably exist, must. The mathematical term is unavoidable. And the answer, the minimum number of dimensions required to guarantee this property, regardless of coloring, is what Graham and his collaborator Bruce Rothschild set out to find in their 1971 paper in the Transactions of the American Mathematical Society. They could not find the exact answer. Nobody has. What they found instead were bounds. The answer, which mathematicians call n star, is at least 6, and at most some enormous number they calculated using a function applied 7 times starting from 12. That upper bound, already incomprehensible, was not what became famous. What became famous was a different, slightly larger upper bound that Graham constructed specifically because it was easier to explain to a non-mathematician. That non-mathematician was Martin Gardner, who wrote the Mathematical Games column in Scientific American. In November of 1977, Gardner published the number in his column, calling it the largest number ever used in a serious mathematical proof. The Guinness Book of World Records picked it up in 1980. And suddenly, a piece of mathematical architecture that existed for a very specific technical reason became a piece of popular culture, stripped of its context, filed under wow, big number, and left there. That filing was a mistake, because the interesting thing about Graham's number was never its size. The interesting thing was what its existence implies about where mathematical truth lives. And to understand that, you need to understand what Ramsey theory actually proves and what happened to the man who invented it. A man who died at 26 years old, 1 year before the most important theorem in the history of mathematics was published, and a decade before the most important machine in the history of computation was conceived. A man whose entire life's work in pure mathematics fits on 8 pages. And those 8 pages changed what we know about the structure of reality. Frank Plumpton Ramsey was born on February 22nd, 1903, in Cambridge, England. His father was the president of Magdalene College. His brother, Michael, would later become the Archbishop of Canterbury, the head of the Church of England, which creates one of the more striking family contrasts in intellectual history, because Frank was a self-described militant atheist who spent his brief career proving that the universe is governed by mathematical necessity, not divine will. He was, by every account, extraordinary. He entered Winchester College as a scholarship student, then Trinity College, Cambridge, where he graduated as senior wrangler, the top mathematics student in his year. At age 19, he produced the first draft English translation of Ludwig Wittgenstein's Tractatus Logico-Philosophicus, one of the most important and difficult philosophy texts of the 20th century. He did not merely translate it. He corresponded with Wittgenstein about it, challenged parts of it, and later personally persuaded Wittgenstein to return to philosophy after Wittgenstein had abandoned the field to teach elementary school in rural Austria. He was elected a Fellow of King's College in 1924 at the age of 21, only the second person in the college's history to receive the honor without having studied there. I am telling you this not because it is interesting background. I am telling you this because Frank Ramsey published exactly 8 pages of pure mathematics in his entire life, and those 8 pages founded an entire branch of combinatorics that now bears his name. And the reason he only published 8 pages is that he died. He fell ill in November of 1929 with what appeared to be jaundice. Doctors performed an exploratory surgery in January of 1930. They found nothing they could fix, but the surgery itself, according to a 2023 case report in Wellcome Open Research, may have been what killed him. He died at Guy's Hospital in London on January 19th, 1930. He was 26 years old. He missed his 27th birthday by 34 days. Think about the timing. Kurt Godel published his incompleteness theorems in 1931, 1 year after Ramsey's death. Alan Turing published his proof of the halting problem in 1936, 6 years later. Ramsey was actively working on the Entscheidungs problem, the decision problem, the very problem Turing would solve. His colleagues at Cambridge believed he would almost certainly have been assigned to Bletchley Park during the war, where Turing and the other code breakers changed the course of history. What he might have contributed, given another 50 years, is one of the great unanswerable questions in the history of science. But what he did contribute in those 8 pages is enough to be unsettling. The paper was called On a Problem of Formal Logic, published in the Proceedings of the London Mathematical Society in 1930, volume 30, pages 264 through 286. Ramsey was not trying to found a new field. He was trying to prove something about formal logic. And on the way there, he needed a lemma, a minor stepping stone result to get past a technical obstacle. That lemma is now called Ramsey's theorem, and it proves something that sounds simple, but is not. It proves that in any sufficiently large structure, complete disorder is mathematically impossible. Here is the simplest example. Imagine you are hosting a party and you invite 6 people. Any 6 people. They can know each other, not know each other, whatever. Ramsey proved that among those 6, you are mathematically guaranteed to find either 3 people who all know each other or 3 people who are all strangers to each other. Not probably, not with high likelihood, guaranteed. It is a logical necessity. The proof is short and elegant. Pick any person, they have 5 relationships. By the pigeonhole principle, at least 3 of those relationships must be the same type, either all friendships or all non-friendships. Say they are friends with persons B, C, and D. If any pair among B, C, and D are also friends, you have your trio of mutual friends. If none of them are friends with each other, then B, C, and D are 3 mutual strangers. Either way, the pattern exists. 5 people are not enough. You can construct a counterexample with 5. But at 6, it becomes unavoidable. The mathematical notation is R of 3, 3 equals 6. R is the Ramsey number, and that simple equation opens a door into one of the most humbling landscapes in all of mathematics. Because once you ask the same question. For larger groups, the numbers become monstrous. R of 4,4, the minimum number of people needed to guarantee 4 mutual friends or 4 mutual strangers, is 18. That was proved in 1955. R of 5,5, the next case, is unknown. After 70 years of effort by some of the best combinatorialists alive, the answer is known only to lie between 43 and 46. The upper bound was improved to 46 as recently as September 2024 by Angeltveit and McKay. The lower bound was pushed to 43 in 2017. The gap is only 3, and closing it may take decades more. Paul Erdos, the most prolific mathematician of the 20th century, captured the difficulty with a thought experiment that has become famous in its own right. Suppose, Erdos said, that aliens land on Earth and demand that humanity compute R of 5,5, or the planet will be destroyed. In that case, he said, we should probably put all our brightest minds and fastest computers on it, and we would probably succeed within a year. But if the aliens demanded R of 6,6, we should attempt to destroy the aliens. That is not a joke about aliens. That is a precise statement about computational complexity. R of 6,6 is known only to lie between 102 and 165. The gap is 63. The search space is so vast that brute force computation is out of the question, even with every computer on Earth running until the heat death of the universe. I want to pause on Erdos for a moment, because he is the other human thread in this story besides Graham and Ramsey, and because his life illuminates something about the nature of mathematical work that most people never see. Paul Erdos was born on March 26, 1913, in Budapest, Hungary. He died on September 20th, 1996, in Warsaw at the age of 83, of a heart attack, while attending a mathematics conference. Between those two dates, he published approximately 1,500 papers with more than 500 co-authors, making him the most prolific mathematician in history. He had no home. He had no job in the traditional sense. He lived out of a suitcase, traveling from university to university, showing up at a colleague's door and announcing, "My brain is open." He would stay for days or weeks, collaborate on problems, and then move on. He owned almost nothing. He gave away most of the money from his prizes. He never married, never had children, never held a permanent academic position after his early career. He was, in a real sense, a person who had decided that the mathematical landscape was more real than the physical one, and had organized his entire life around the conviction that the most important thing a human being could do was to explore that landscape. Erdos had a phrase he used for the most elegant proofs. He said they came from the book, an imagined volume in which God kept the perfect proof of every theorem. Erdos was an atheist. When asked about this, he said he did not need to believe in God to believe in the book. The book, in Erdos's usage, was not a religious concept. It was a Platonic one. The perfect proofs exist. They are out there. The job of mathematicians is to find them. That belief, that mathematical truth, exists independently and is waiting to be discovered rather than invented, was not incidental to Erdos's work. It was the engine of it. He worked on Ramsey theory for decades, and the problems he posed in that field remain among the most important open questions in combinatorics. His relationship with Graham was not just professional. It was, according to multiple accounts, one of the defining friendships in both of their lives, a friendship conducted almost entirely in the language of mathematics, across continents, over 4 decades. And the numbers that Erdos and Graham chased together, the Ramsey numbers, have a property that should trouble you. They are finite. They are specific. Each one has an exact value, and we cannot compute most of them. Not because we lack the talent or the technology, but because the computational resources required exceed anything the physical universe can provide. The values are there. They are determined. They are as fixed as the speed of light, and most of them are permanently beyond our reach. Think about what that means for the relationship between mathematical truth and physical reality. There are true facts about finite numbers, ordinary integers, nothing exotic that the physical universe lacks the capacity to verify. Not because the facts are uncertain, because the universe is too small. And here is where it gets worse. Because Ramsey theory does not just say that patterns exist in large structures. It says that patterns must exist. The universe does not get a vote. If a structure is large enough, the order is there whether anyone looks for it or not. Mathematics does not describe the patterns. Mathematics forces them into existence. The structure has no choice. That word, forces, is the one I want you to sit with, because it changes the entire relationship between math and the world. If you think of math as a language, a tool, a description, then patterns in nature are something math notices after the fact. But Ramsey theory says the opposite. The patterns are not observed, they are compelled. The mathematics does not follow the structure follows the mathematics. And in March of 2003, something happened that should have made front-page news and did not. 4 mathematicians, Marcelo Campos, Simon Griffiths, Robert Morris, and Julian Sahasrabudhe, published a proof that the diagonal Ramsey number R of k, k is bounded above by 3.993 to the k. That might not sound like much, but the previous upper bound, 4 to the k, had been established by Erdos and shatters. In 1935, it had stood for 88 years. Nearly a century of mathematicians had tried to improve it. None had succeeded. The base of the exponential had been 4 since before World War II, through the Manhattan Project, through the moon landing, through the invention of the internet, through the development of quantum computers. And then, in a single paper, 4 researchers showed it could be made strictly less than 4. Yuval Wigner of Tel Aviv University said he was, and I am quoting directly here, literally shaking for half an hour when he saw the result. By July of 2004, the bound had already been tightened further to 3.8 to the k by Gupta, Ndiaye, Norin, and Wei. After 88 years of stasis, the dam broke. But here is the thing that nobody said out loud. The breakthrough confirmed something that was already implicit in Ramsey theory from the beginning. The patterns that Ramsey theory guarantees are not products of the physical world. They exist in a mathematical structure that transcends the physical world entirely. R of 5,5 has a definite value right now, today, whether or not any human being or any computer ever computes it. It was true before Frank Ramsey was born. It was true before the Earth existed. It will be true after every star burns out. The mathematics is not waiting for us to discover it. It is already there, and the man who first proved this, who showed that mathematical structure compels order into existence, whether anyone is watching or not, died in a London hospital at 26 because a surgeon opened him up looking for something wrong, and the surgery itself may have been what killed him. A man who was on the verge of some of the most important intellectual achievements of the 20th century, cut off by a medical decision that a 22,003 paper suggests might have been a mistake. Frank Ramsey did not live to see what his 8 pages would become. He did not live to see Graham's number, which exists because of the field he created. He did not live to see Godel prove that mathematical truth exceeds the reach of any formal system, which would have fascinated him. He did not live to see Turing build the theoretical foundations of computation on the very problem Ramsey himself was working on when he died. But the mathematics he discovered does not care about any of that. It was true before he was born. It was true after he died. And it will remain true regardless of whether anyone remembers his name. That is not a comforting thought. That is the thought and the number that his work eventually produced. The number that Ronald Graham calculated 4 decades later is where the story stops being about history and starts being about the nature of reality itself. Because to understand what Graham's number actually is, you need to walk through its construction step by step. And each step is going to make the previous one feel like nothing. Ronald Graham was not what you would expect from the man who produced the largest number in the history of mathematics. He was 6'2", spoke fluent Mandarin Chinese, was colorblind, could juggle 6 balls simultaneously, and held the California State Trampoline Championship. He was also, according to multiple sources, an accomplished unicyclist who once performed with Cirque du Soleil. He was elected president of the International Jugglers Association in 1972. There is a widely circulated photograph showing him juggling 12 balls. The photograph is fake. Even Ronald Graham had limits, though in his case, the limits were genuinely difficult to locate. He was born on October 31st, 1935, in Taft, California. His father worked in the oil fields. The family moved constantly between Georgia, Florida, and California. At 15, he won a Ford Foundation scholarship to the University of Chicago, where an acrobatics class called acrotheater ignited a lifelong obsession with physical performance that never left him. He transferred to UC Berkeley, became the state trampoline champion, but did not initially complete a degree. He enlisted in the Air Force in 1955, served as a communications specialist in Fairbanks, Alaska, earned a bachelor's degree in physics from the University of Alaska, and then returned to Berkeley for a master's in 1961 and a PhD in mathematics in 1962 under the supervision of Derek Lehmer. During graduate school, Graham and 2 other students formed a professional trampoline troupe called the Bouncing Bears. They performed at schools and supermarket openings to pay tuition. This is a man who funded his path to the largest number in mathematical history by doing backflips in parking lots. He joined Bell Laboratories in 1962, the legendary research institution where the transistor was invented, where information theory was born, where the cosmic microwave background radiation was accidentally discovered. Graham spent 37 years there, eventually becoming chief scientist of AT&T Labs. His work spanned telephone call routing, scheduling theory, and discrete mathematics. In 1999, he moved to the University of California, San Diego, as the Irwin and Joan Jacobs Endowed Professor. His intellectual partnership with Paul Erdos is one of the great stories in 20th century mathematics. They met at a number theory conference in Boulder, Colorado in 1963. Erdos who was decades older, promptly beat Graham at ping pong. Graham, who was apparently the kind of person who took this personally, joined a club, practiced obsessively, and eventually won both the Bell Labs Championship and a New Jersey state title. They published approximately 30 joint papers. Graham kept a room in his home permanently reserved for Erdos during his visits. Graham's Erdos number was 1, meaning he co-authored a paper directly with Erdos, and he is credited with popularizing the concept of the Erdos number itself. He married the mathematician Fan Chung in 1983. They co-authored over 90 papers together. He died on July 6, 2020, at the age of 84 of bronchiectasis in La Jolla, California. I spent an unreasonable amount of time reading about Ronald Graham, and the thing that strikes me most is the contrast. This was a man who lived in his body, who juggled, who bounced, who performed triple somersaults on a trampoline into his 60s, and he produced a number that no body, no planet, no universe can contain. The most physical mathematician of his generation created the most unphysical object in the history of thought. That irony is either meaningless or it is the point. Now, the number. To understand what Graham's number is, you need to understand a notation system invented by Donald Knuth, the computer scientist, in a 1976 paper in Science magazine titled Mathematics and Computer Science, Coping with Finiteness. Knuth introduced the up arrow notation to describe a hierarchy of operations, where each level is the iteration of the one below it. You already know the first 3 operations in this hierarchy, even if you have never seen them written this way. Multiplication is repeated addition. 3 times 3 means 3 plus 3 plus 3. That gives you 9. Exponentiation is repeated multiplication. 3 to the 3rd power means 3 times 3 times 3. That gives you 27. Both of these are familiar. Both of these are manageable. Both of these are, for the purposes of what comes next, essentially 0. The 3rd operation in the hierarchy is called tetration. It is repeated exponentiation. In Knuth's notation, 3 double up arrow. 3 means 3 raised to the power of 3 raised to the power of 3. You evaluate from the top down. 3 to the 3 is 27. 3 to the 27th power is 7,625,597,487. Just 2 levels of the hierarchy, just 1 additional arrow, and we have already left the realm of numbers you encounter in daily life. But we are still on the ground floor. 3 triple up arrow. 3 means 3 double up arrow. 3 double up arrow. 3. But the inner 3 double up arrow 3 is itself that 7 trillion digit number I just described. So 3 triple up arrow 3 is a power tower of 3s that is 7.6 trillion levels tall, not 7.6 trillion. A power tower 7.6 trillion levels tall. If you wrote each 3 in the tower as a single millimeter of text, the tower of 3s would stretch from Earth, past the nearest star, past the edge of the Milky Way, past the nearest galaxy cluster, and past the edge of the observable universe. And you would not be close to done. You would not be 1/100000th of 1/10000000th of the way to writing down the number that this tower of 3s evaluates to. The number of digits in the result dwarfs the number of particles in the observable universe by a margin that itself dwarfs the number of particles in the observable universe. That is 3 arrows, 3 up arrow, up arrow, up arrow, 3. 4 arrows is tetration of tetration. It takes the previous incomprehensible result and uses it as a parameter in a new operation that iterates the previous operation. If 3 arrows already escapes the observable universe by a margin that cannot be expressed, 4 arrows escapes the concept of escaping the observable universe. The human brain has no architecture for this. You are not failing to imagine the number because you are not trying hard enough. You are failing because the number exceeds the information capacity of any physical system that could exist in this universe. And now you are ready for Graham's number. Take G1, that is 3, with 4 arrows pointing at 3. 3, quadruple up arrow 3, already incomprehensibly beyond anything expressible. Now define G2 as 3, with G1 arrows pointing at 3, not 4 arrows. A number of arrows so large that the number itself exceeds the Bekenstein bound for the observable universe. Then G3 is 3, with G2 arrows pointing at 3. Continue this for 64 layers. Graham's number is G64. I need to pause here because I think the sheer scale of this gets lost in the notation. Each layer does not add a fixed amount. Each layer applies an entirely new operation to the result of the previous layer, using that result as the definition of the operation. G2 is not bigger than G1, the way a trillion is bigger than a billion. G2 is bigger than G1 the way exponentiation is bigger than addition. Except the comparison between G1 and G2 is itself exponentially understating the gap, because each new layer does not merely increase the number, it increases the rate at which the number increases, which increases the rate at which the rate increases, which increases the rate of increase of the rate of increase of the rate of increase. And this recursion of increasing rates continues for a number of levels that is itself G1, which itself cannot be written down. And there are 64 layers of this. That is Graham's number, a number so large that the physical universe, all of it, every proton, every photon, every Planck volume of space, every quantum of energy since the Big Bang, is not sufficient to contain even a meaningful description of where the number sits in the hierarchy of large numbers. You cannot get to Graham's number from any physical quantity by any physical operation repeated any physical number of times. But here is the part that I still do not know how to think about. Despite all of this, we know facts about it. We know it is odd. We know it is divisible by 3. We know its last 500 digits with absolute certainty. Marco Ripper published an exact solution for the stable trailing digits of Graham's number in a 2024 paper on Arxiv. The mathematical properties of this number are as fixed, as determinate, as objectively real as the charge of an electron. Think about what that means. We can prove facts about an object that the entire physical universe is too small to contain. If mathematics were just something humans invented to keep track of sheep, that should not be possible. The fact that it is possible tells you something about where you actually are. And Graham's number, for all its incomprehensible enormity, is not even close to the largest number mathematicians have encountered. It is not close to the edge of what mathematics contains. It is not close to the ceiling. There is no ceiling. In the hierarchy of large numbers that mathematics has produced, Graham's number occupies a position that is, and I want to be precise about this, low, not middling, not modest. Low. It is a foothill at the base of a mountain range that extends upward without limit. And the mountains behind it are so tall that Graham's number, from their perspective, is indistinguishable from 0. The first number that should recalibrate your sense of scale is called tree of 3. It comes from a problem studied by Harvey Friedman, a logician at Ohio State University, beginning in the early 1980s. The problem is about sequences of trees, the mathematical kind, not the botanical kind. A rooted tree with labeled vertices you are allowed to use at most n different labels. Tree of n is the length of the longest possible sequence of such trees, where each tree t sub I has at most I vertices, and no earlier tree in the sequence is homeomorphically embeddable in a later one. Homeomorphic embedding is a specific technical relationship between trees, and the constraint is that the sequence cannot exhibit a certain kind of redundancy. Tree of 1 equals 1. You can only make a one-vertex tree with one label, and then the sequence must stop. Tree of 2 equals 3. With 2 labels, you can make a sequence of 3 trees before the embedding constraint forces termination. Tree of 3 is a number so large that Graham's number is, in the technical literature, described as unnoticeable. Beside it, I want to be clear about what that means. It does not mean tree of 3 is a lot bigger than Graham's number, the way a galaxy is a lot bigger than an atom. It means that if you try to locate Graham's number on the scale between 0 and tree of 3, Graham's number would be so close to 0 that no meaningful distinction could be drawn. The function that takes you from numbers expressible with Knuth's up arrows, which is where Graham's number lives, to numbers in the tree range is not an exponential leap. It is not a leap at all, because the word leap implies you start somewhere recognizable and land somewhere recognizable. And when you go from Graham's number to tree of 3, you start at effectively nothing and arrive at something for which no existing language of comparison applies. In the fast-growing hierarchy, which is the standard tool mathematicians use to classify growth rates, Graham's number sits at roughly f sub omega plus 1 of 64. Tree of 3 corresponds to an ordinal in the vicinity of the small Veblen ordinal, which is so far beyond omega plus 1 that describing the gap requires transfinite ordinal arithmetic that most working mathematicians never encounter. And there is a number beyond tree of 3. In 2006, Friedman defined a function called SSCG, which counts maximum length sequences of simple subcubic graphs under a similar embedding constraint. SSCG of 3 exceeds TRERERER of tree of 3, nested tree of 3 times. You take the tree function, which already annihilated Graham's number, and you iterate it a number of times equal to tree of 3, and you are still not at SSCG of 3. Adam Goucher proved this. It is published mathematics. But even SSCG of 3 is computable. Given unlimited time and resources, you could in principle calculate it. The truly terrifying boundary in the landscape of large numbers is the one that separates computable numbers from uncomputable ones. And the function that crosses that boundary is the Busy Beaver. The Busy Beaver function, BB of n, was defined by Tibor Rayo in a 1962 paper in the Bell System Technical Journal. It asks a question that sounds almost childishly simple. Take a Turing machine, the theoretical model of computation that Alan Turing defined in 1936, with n states and a 2-symbol alphabet. There are finitely many such machines. Some of them halt, meaning they eventually stop running. Some of them run forever. Among the ones that halt, which one takes the most steps before halting? BB of n is that maximum number of steps. For small values, the answers are modest. BB of 1 is 1. BB of 2 is 6. BB of 3 is 21. BB of 4 is 107. These were established through exhaustive analysis of all possible machines with that many states. BBB of 5 was unknown for decades. It was one of the longest-standing open problems in computability theory. And then, on July 2nd, 2004, the Busy Beaver Challenge, a collaborative online project founded by Tristan Sterrin in 2002, announced that BB of 5 equals 47,176,870. The proof was formally verified using the Coq proof assistant. It took the coordinated effort of dozens of researchers and automated verification systems to establish the halting behavior of every single 5-state Turing machine. 47 million. That is a number you can write on a napkin. It is a number your phone's calculator can handle, and it required the entire machinery of modern computability theory and formal verification to pin down. BB of 6 is unknown, and the reason it is unknown is not that we have not tried hard enough. A specific 6-state Turing machine has been constructed whose halting behavior depends on the truth or falsity of the Collatz conjecture, one of the most famous unsolved problems in mathematics. To know BB of 6, you may need to resolve questions that have resisted every mathematical technique developed in the last century. I need to slow down here because the Collatz connection is worse than it sounds, and most accounts of the Busy Beaver skip past it too quickly. The Collatz conjecture is this: take any positive integer. If it is even, divide it by 2. If it is odd, multiply by 3 and add 1. Repeat. The conjecture says that no matter what number you start with, you will eventually reach 1. It has been verified for every starting number up to roughly 10 to the 20th power. It has been open since 1937. Erdos himself said that mathematics is not yet ready for such problems. Terence Tao, arguably the greatest living mathematician, proved in 2019 that the conjecture is true for almost all numbers in a precisely defined statistical sense, but could not prove it for all of them. And there is a 6-state Turing machine, a machine with 6 states and a 2-symbol alphabet, which you could describe on the back of a postcard, whose halting behavior is equivalent to the Collatz conjecture being false. If the Collatz conjecture is true, the machine runs forever. If it is false, the machine halts. So knowing BB of 6, knowing the maximum number of steps any 6-state machine takes before halting, would tell you whether the Collatz conjecture is true or false. Because if BB of 6 is, say, some specific value n, and the Collatz machine has not halted after n steps, then it never will, and the conjecture is true. A postcard-sized machine encodes one of the deepest unsolved problems in mathematics. That is not a coincidence. It is a structural feature of computation. Simple machines can encode arbitrarily complex mathematical questions. And the Busy Beaver function, which asks for the maximum runtime of machines at each level of complexity, is therefore a function that contains, compressed into its values, the answers to virtually every open question in mathematics. BB of 27 encodes the Goldbach conjecture. BB of 744 encodes the Riemann hypothesis. BB of 745 encodes the consistency of Zermelo-Fraenkel set theory. The function is a mathematical oracle, and it is an oracle that provably cannot be consulted. And here is where Godel enters the story and changes everything. Kurt Godel was born on April 28, 1906, in Brunn, Austria-Hungary, which is now Brno in the Czech Republic. He died on January 14, 1978, in Princeton, New Jersey, of starvation because his paranoia about being poisoned had become so severe that he refused to eat food unless his wife Adele prepared it. And when Adele was hospitalized, he simply stopped eating. He weighed 65 pounds at the time of his death. The greatest logician since Aristotle, the man who proved that mathematical truth exceeds the reach of any formal system, starved to death because he could not trust the world to be what it appeared to be. If you want a metaphor for the relationship between the human mind and mathematical reality, you could do worse than that. In 1931, Godel published 2 theorems that demolished the foundations of early 20th century mathematics. The first incompleteness theorem proves that any consistent formal system capable of expressing basic arithmetic contains true statements that it cannot prove. The second proves that such a system cannot prove its own consistency. These theorems ended the Hilbert program, which had aimed to place all of mathematics on a secure, complete, consistent axiomatic foundation. Godel showed that no such foundation exists. Mathematics is too large, too wild, too deep for any finite system of axioms to capture. And the Busy Beaver function is where Godel's theorems collide with concrete numbers. For any consistent formal system, there exists a value of n beyond which BB of n is independent of that system, meaning the system cannot prove the value of BB of n, even though BB of n has a definite, specific value. This is not a limitation of computing power or human ingenuity. This is a limitation of logic itself. Specific Turing machines have been constructed whose halting behavior is equivalent to the consistency of Zermelo-Fraenkel set theory, the axiomatic system that underlies virtually all of modern mathematics. If ZFC is consistent, which nearly all mathematicians believe but cannot prove, then these machines do not halt. And their non-halting is a true statement that ZFC cannot establish. The Busy Beaver function grows faster than any computable function, faster than tree, faster than SSCG, faster than any function that any algorithm, no matter how clever, running on any computer, no matter how powerful, could ever produce. It crosses the boundary between the knowable and the unknowable. It lives in a mathematical territory that provably exceeds the reach of any finite system, including any system that could be instantiated in the physical universe. And there are numbers beyond even the Busy Beaver function. On January 26, 2007, at MIT, 2 philosophers named Agustin Rayo and Adam Elgar held what they called the big number duel. The rules were simple. Each contestant took turns writing a description of a number on a blackboard. The descriptions had to be well defined, and whichever number was larger, won. Rayo won by defining what is now called Rayo's number, the smallest positive integer larger than any number that can be named by an expression in the language of first-order set theory using 10 to the 100th power symbols or fewer. The number itself is not computable, not even in principle, not even with unlimited resources. And Rayo himself acknowledged in 2020 that its well-definedness depends on philosophical assumptions about the interpretation of set theory that are genuinely contested. I want to stop here and make sure you feel the weight of the sequence we just walked through. Graham's number was the largest number used in a serious mathematical proof when it was published. It is a fixed, specific, finite integer with deterministic properties. It lives in a particular spot in the hierarchy of mathematical objects. Tree of 3 makes Graham's number look like 0. SSCG of 3 makes tree of 3 look like 0. The Busy Beaver function makes all of them look computable, which they are, but from the Busy Beaver's perspective, computability is a weakness, a limitation, a ceiling that the Busy Beaver left behind. And Rayo's number makes the Busy Beaver function look like a particularly ambitious counting exercise. Each of these numbers is real. Each has determinate properties. Each exists in the mathematical landscape with the same ontological status as the number 7. And none of them, not one, can be physically instantiated anywhere in the observable universe. The universe is not big enough, not by factors of size that we lack words for. I want to make sure the weight of that hierarchy lands properly, because the notation can make it feel abstract, and it is not abstract. It is the most concrete thing I have ever encountered. Imagine you are standing on a number line. At your feet is the number 1. A step away is 2. You can walk comfortably up to 1,000 in a few minutes if you count quickly. 1,000,000 is a brisk walk. 1,000,000,000 is a long day. The number of atoms in the observable universe, roughly 10 to the 80th, is far away, incomprehensibly far. But at least you can point in its direction and say, it is that way and it is finite. And, in principle, I could walk there. Graham's number is not on that number line. I do not mean it is very far along the number line. I mean the number line you are imagining, the one that extends from 1 to infinity, the one that contains every number you have ever heard of, including the number of atoms in the universe, and the Googleplex, and the number of possible chess games, and every other large number that has ever been cited in any popular science context. That entire number line, from 1 to any number you can name or imagine or describe, is, from the perspective of Graham's number, a point, a single point at the origin, indistinguishable from 0. You are not walking to Graham's number. You are not flying. You are not traveling at the speed of light. There is no physical process, no chain of operations starting from any physical quantity that reaches Graham's number. It lives in a region of the mathematical landscape that the physical universe does not have roads to. And Tree of 3 is so far beyond Graham's number that the same thing is true again. Graham's number, from Tree of 3's perspective, is a point at the origin, indistinguishable from 0. And SSCG of 3 does the same thing to Tree of 3. And the Busy Beaver function, for large enough inputs, does the same thing to all computable functions simultaneously, because it grows faster than any of them, by definition, by proof, by the structure of mathematics itself. The hierarchy does not stop. There is no largest number. There is no fastest growing function. There is no ceiling. The mathematical landscape extends upward without limit, each level making the previous one vanish into insignificance. And the entire physical universe, every particle, every field, every quantum of energy, every Planck length of space, occupies a negligible sliver at the very bottom of this structure. That is not a metaphor. That is what the Bekenstein bound, combined with the existence of these numbers, formally implies. The question this raises is the question the rest of this story is about. If these objects exist, and they do, and they have properties, and they do, and they cannot exist inside the physical universe, and they cannot, then where do they exist? And the answer that physicists have been quietly, carefully, reluctantly arriving at for the last 60 years is the one you were never told. In 1960, a Hungarian-American physicist named Eugene Wigner published a paper in Communications in Pure and Applied Mathematics, Volume 13, Number 1, pages 1 through 14. The paper was called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Wigner had won the Nobel Prize in Physics in 1963 for his contributions to the theory of the atomic nucleus and elementary particles. Though the paper preceded the prize by 3 years, he was born in Budapest in 1902 and died in Princeton in 1995 at the age of 92. And the paper he wrote in 1960 is, in my opinion, one of the most important documents in the history of human thought that almost nobody has read. Wigner's argument was not complicated. He observed that mathematicians develop concepts for their own reasons, for aesthetic pleasure, for the internal logic of the field, for what he called the mathematician's ingenuity and sense of formal beauty. These concepts are created without any reference to the physical world. They are products of pure thought, developed because they are interesting, elegant, or internally consistent. And then, years or decades or centuries later, these concepts turn out to describe the physical world with an accuracy that, in Wigner's words, borders on the mysterious. He gave specific examples. Isaac Newton formulated the law of universal gravitation from, as Wigner put it, very scanty observations. The law was a mathematical relationship, and when it was tested against the actual motions of planets, moons, and comets, it proved, again in Wigner's words, accurate beyond all reasonable expectations. The number pi, a ratio discovered through pure geometry, appears in statistical distributions that describe the behavior of populations, in the equations governing the distribution of prime numbers, and in the fundamental constants of quantum mechanics, despite having no obvious reason to be present in any of these contexts. Complex numbers, which were invented as a mathematical curiosity to solve polynomial equations and were considered fictitious for centuries, turned out to be essential to the formulation of quantum mechanics, the most precise physical theory ever constructed. Wigner called this correspondence a wonderful gift which we neither understand nor deserve. He did not resolve the mystery. He simply named it, and the name stuck. The unreasonable effectiveness of mathematics has been discussed, debated, and largely avoided by the physics community for the 66 years since that paper was published. Discussed because the evidence is undeniable. Debated because the implications are uncomfortable. And avoided because the most straightforward explanation, the one that makes the evidence cohere, is the one that nobody wants to say out loud in a professional context. The evidence has only gotten stronger since Wigner wrote. In 1928, Paul Dirac derived an equation that unified quantum mechanics and special relativity. The Dirac equation was a piece of pure mathematics. Dirac was trying to find a wave equation that was consistent with both the probabilistic framework of quantum mechanics and the relativistic requirement that the laws of physics look the same in all inertial reference frames. The equation he found had a peculiar feature. It had two sets of solutions. One set described electrons with positive energy, which was expected. The other set described particles with the same mass as electrons, but with positive charge and negative energy, which was not expected and which no one had ever observed. Dirac could have dismissed these solutions as mathematical artifacts, unphysical, a quirk of the formalism. He did not. He proposed that these solutions described a new kind of particle, a mirror image of the electron. In 1932, Carl Anderson, working with a cloud chamber at Caltech, photographed a track of exactly such a particle. He called it the positron. It had the mass of an electron and a positive charge, precisely as the mathematics required. The mathematics came first, the physical reality followed, not the other way around. In 1964, 3 independent groups of physicists, Peter Higgs in Edinburgh, Robert Brout and Francois Englert in Brussels, and Gerald Guralnick, Carl Hagen, and Tom Kibble in London, proposed that the mathematical framework of gauge symmetry in particle physics required the existence of a new field permeating all of space, and that excitations of this field would manifest as a new particle. The prediction was purely mathematical. It followed from the structure of the equations. No one had observed the particle. No one had evidence for the field. The mathematics simply said it had to be there. 48 years later, on July 4, 2012, CERN announced that the Large Hadron Collider, a 27-kilometer ring of superconducting magnets buried beneath the Swiss-French border, had detected a particle consistent with the Higgs boson at a mass of approximately 125 gigaelectronvolts. The statistical significance was 5 sigma, meaning the probability of the signal being a random fluctuation was less than 1 in 3.5 million. 48 years. The math said the particle had to exist in 1964. The particle was confirmed to exist in 2012. The universe obeyed the mathematics, not immediately, not approximately, but precisely, across nearly half a century of waiting. And it gets worse. In 1916, Albert Einstein published his general theory of relativity, which described gravity not as a force, but as the curvature of space-time caused by mass and energy. The field equations of general relativity, a set of 10 coupled nonlinear partial differential equations, predicted the existence of gravitational waves, ripples in the fabric of space-time itself that propagate at the speed of light. Einstein himself was ambivalent about whether these waves were real or mathematical artifacts. The physics community debated the question for decades. Some argued the waves were a coordinate effect, a product of the mathematical formalism rather than a physical phenomenon. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time. The signal came from 2 black holes that had spiraled into each other, 1.3 billion light-years away, and the waveform matched the predictions of general relativity to a precision that the LIGO team described as extraordinary. The detection was announced on February 11, 2016, 99 years after the mathematics predicted them. Gravitational waves were confirmed to be real. 99 years. And there is more. Maxwell's equations, formulated in 1865, predicted the existence of electromagnetic waves traveling at the speed of light. Heinrich Hertz confirmed them experimentally in 1887. 22 years later, Murray Gell-Mann's mathematical SU-3 symmetry group, proposed in 1962, predicted the existence of a particle called the omega minus, with a specific mass, charge, spin, and set of decay products. The particle was discovered at Brookhaven National Laboratory in 1964. 2 years later, with every predicted property matching exactly. In every one of these cases, the pattern is the same. A mathematician or physicist writes down equations. The equations followed to their logical conclusions, predict the existence of something that has never been observed. Years or decades pass, and then the thing is found, exactly where the mathematics said it would be. This pattern has repeated so many times across so many domains of physics that at some point you have to stop treating it as coincidence and start asking what it means. You have to ask the question that Wigner asked in 1960, and that the physics community has been carefully, studiously, professionally avoiding ever since. Why does mathematics work? Not, how is math useful? That question is trivial. Math is useful because humans evolved to recognize patterns, and mathematics formalizes pattern recognition. Fine. That explains why counting works. That explains why basic arithmetic is handy for building bridges. It does not explain why abstract mathematical structures, invented for purely aesthetic reasons, turn out to describe the deepest features of physical reality with extraordinary precision. It does not explain why the universe appears to be a mathematical structure rather than a physical system that merely obeys mathematical regularities. It does not explain why Dirac's equation, a piece of pure formalism, predicted the existence of matter that no one had imagined. It does not explain why Gell-Mann's symmetry group, an abstract algebraic object, predicted a particle with the exact mass and quantum numbers that was subsequently confirmed. It does not explain any of the examples Wigner cited or the dozens of examples that have accumulated since. The standard responses are inadequate. Some physicists say that math works because we select for the math that works. We remember the equations that predicted real phenomena and forget the ones that did not. This is the selection bias argument, and it fails on inspection. The ratio of mathematical predictions that turned out to be correct to mathematical predictions that turned out to be wrong in mature physical theories is not 50-50. It is overwhelmingly skewed toward correctness. The standard model of particle physics, a mathematical framework, predicted the existence of the W and Z bosons, the top quark, the Higgs boson, and dozens of other particles and interactions, and has been confirmed to a precision of better than 1 part in 10 billion in some measurements. The theory is not occasionally right by luck. It is systematically, precisely, disturbingly right about things that no one had observed when the predictions were made. Some physicists say that math works because humans are wired to think mathematically, and we project mathematical structure onto a universe that does not inherently possess it. This is the constructivist argument, and it runs directly into the problem that Graham's number poses. If mathematics is a human construction, then mathematical objects should be limited by human cognitive architecture, or, at most, by the physical resources available for computation. But Graham's number has determinate properties that no human brain, no physical computer, and no possible physical system can verify. The properties are there anyway. They were there before humans existed. They will be there after humans are extinct. Constructivism cannot account for this, and some physicists say that we should stop asking the question. That mathematics is a tool, it works, and wondering why it works is philosophy, not physics. This is the shut up and calculate argument, and it is, in the most precise sense, a refusal to follow the evidence. There are a few physicists who have been willing to follow it. Roger Penrose, born August 8, 1931, who won the Nobel Prize in Physics in 2020 for proving that black hole formation is a robust prediction of general relativity, has argued for mathematical Platonism throughout his career. In his 2004 book, The Road to Reality, Penrose described what he calls the three worlds framework. There is the Platonic mathematical world, which contains all mathematical truth. There is the physical world, which appears to be described by a subset of that mathematical truth. And there is the mental world, which emerges from the physical world and somehow has access to the mathematical world. Three worlds, three mysteries connecting them. Penrose has written, and I am paraphrasing from The Emperor's New Mind, that when one sees a mathematical truth, one's consciousness makes direct contact with the Platonic world of mathematical ideas. Max Tegmark, born May 5, 1967, in Stockholm, a professor of physics at MIT, has taken the argument further than anyone else with academic credentials has been willing to go. In his 2014 book, Our Mathematical Universe, and in a 2007 paper on Arxiv, Tegmark proposed what he calls the mathematical universe hypothesis. The claim is this: the physical universe is not merely described by mathematics. The physical universe is a mathematical structure, not metaphorically, not approximately, literally. Tegmark's argument proceeds in steps. If you remove from your description of the universe everything that is not mathematical, every label, every name, every qualitative description, what remains? The mass of the electron is a number. The charge of the electron is a number. The spin is a number. The space-time coordinates of every particle are numbers. The forces between them are mathematical relationships. The laws governing their evolution are mathematical functions. When you strip away everything that is not mathematical, what is left is still a complete description of the universe. Nothing has been lost. There is no residue, no non-mathematical stuff that the equations fail to capture. If the mathematical description is complete, Tegmark asks, then what exactly is the non-mathematical physical reality that the mathematics is supposed to be describing? What would it mean for such a thing to exist? And his answer is that it would not mean anything, because the mathematical structure is the only thing that is there. This is not a popular position. George Ellis of the University of Cape Town has called it untestable. Peter Woit of Columbia University has called it not even wrong. Edward Frenkel of Berkeley has argued that it is incompatible with Godel's incompleteness theorems, because if the universe is a mathematical structure, Godel guarantees it contains truths about itself that it cannot prove, which would mean there are facts about reality that are in principle inaccessible from within reality. Tegmark himself acknowledges this objection and considers it a feature rather than a bug. But here is what matters for our purposes. The objections to Tegmark are not about the evidence. They are about the implications. Nobody disputes the unreasonable effectiveness of mathematics. Nobody disputes that mathematical predictions have an extraordinary track record of being confirmed by experiment. Nobody disputes that Graham's number has determinate properties despite being physically unrealizable. The objections are all variations of that cannot be right, because it would mean, followed by an implication that the objector finds too uncomfortable to accept. That is not a scientific argument, that is a psychological one. And Godel, the man who proved that mathematical truth exceeds any formal system, was the most committed mathematical Platonist of the 20th century. He believed that mathematical objects are as real as physical objects, that they exist independently of human minds, and that the human mind has a faculty analogous to perception that allows it to access mathematical truth directly. He did not believe this despite his incompleteness theorems. He believed it because of them. If mathematical truth can exceed the reach of any formal system, then it cannot be a product of formal systems. It must exist independently, in a realm that formal systems can only partially access. And if Tegmark is even partially right, then the answer to every question you have ever asked about why the universe works the way it does is the same answer, because mathematics requires it, not permits it, requires it. And you are about to see what that means for you personally, because there is one more piece of this puzzle, and it is the piece that ties Graham's number, the Bekenstein bound. Ramsey theory, Godel's theorems, and Tegmark's hypothesis into a single, coherent, deeply unsettling picture. And it has to do with the relationship between information, physics, and the nature of existence itself. Jacob Bekenstein was born on May 1st, 1947, in Mexico City. His family moved to Israel when he was a teenager. He did his doctoral work at Princeton under John Archibald Wheeler, the same Wheeler who coined the terms black hole and wormhole and it from bit, the same Wheeler who spent his career arguing that information is the fundamental substance of reality. Bekenstein's thesis, completed in 1972, proposed something that his own advisor found disturbing and that Stephen Hawking publicly rejected. Bekenstein argued that black holes have entropy, and that the entropy, the information content, is proportional not to the volume of the black hole, but to the area of its event horizon. Hawking rejected this, because if black holes have entropy, they must have temperature, and if they have temperature, they must radiate, and black holes, by definition, do not let anything escape. But in 1974, Hawking performed his own calculation and discovered, to what, by all accounts, was his genuine astonishment, that black holes do radiate. Hawking radiation. The combined Bekenstein-Hawking entropy formula became one of the most important results in theoretical physics, and the implication of that formula was staggering. The maximum information that can be stored in any region of space is proportional to the surface area of the boundary of that region, not its volume. This is the holographic principle, proposed by Gerard Knuth in 1993, and given precise string-theoretic form by Leonard Susskind in 1995. It means that in some deep sense, the three-dimensional universe you perceive is encoded on a two-dimensional surface. The third dimension is, in a specific technical sense, a projection. Wheeler himself, Bekenstein's doctoral advisor, had a phrase for what all of this implied. He called it from bit, the idea that every physical quantity, every particle, every force, every space-time curvature derives its existence from information. Not matter, not energy. Information, bits, mathematical relationships. Wheeler wrote this in a 1990 paper for the Proceedings of the Santa Fe Institute, and the specific sentence that matters is this, one which I will paraphrase because its meaning is too important to lose in the original academic prose. Wheeler argued that the physical world, at its deepest level, is not made of stuff. It is made of answers to yes or no questions. Every measurement, every observation, every physical fact is, at bottom, a binary choice, a bit. This was not mysticism. This was John Archibald Wheeler, who supervised Richard Feynman's doctoral thesis, who co-authored the standard textbook on general relativity with Charles Misner and Kip Thorne, who was one of the architects of the atomic bomb at Los Alamos. This was a man with impeccable credentials in mainstream physics, and he spent the last 2 decades of his career arguing that information is more fundamental than matter, that the laws of physics are derivable from the structure of information, and that the physical universe emerges from a mathematical substrate rather than the other way around. He was saying in the 90s what Tegmark would say more explicitly in 2007. And he was saying it because the Bekenstein bound, derived by his own student, pointed in that direction. If the information in a region of space is proportional to the area of its boundary, then the 3-dimensional physical world inside that boundary is, in a precise sense, less fundamental than the 2-dimensional information on its surface. The information is primary, the physicality is derived, and the Bekenstein bound, the formula that tells you the maximum information in a region, is what connects Graham's number to the deepest questions in physics. Because the bound tells you that the observable universe, all of it, can contain at most approximately 10 to the 122nd power bits of information. Seth Lloyd calculated this in a 2002 paper in Physical Review Letters titled Computational Capacity of the Universe. The universe, since the Big Bang, has performed at most 10 to the 120th power elementary operations on 10 to the 90 bits. Graham's number exceeds these limits by margins that the limits themselves cannot express. Tree of 3 exceeds them by margins that Graham's number cannot express. And the Busy Beaver function, for sufficiently large inputs, exceeds them by margins that no computable function can express. This means that the mathematical landscape contains objects, real objects, with determinate properties, that the physical universe is not merely too small to contain, but that the physical universe lacks the computational capacity to even verify. The universe cannot check whether certain mathematical statements are true, not because it has not tried, not because it has not had enough time, because Godel's theorems, combined with the Bekenstein bound and the holographic principle, prove that the information processing capacity of the physical universe is fundamentally, permanently, physically insufficient to access certain mathematical truths. The mathematical structure is larger than the physical universe, not in the sense of spatial size, in the sense of information, complexity, and depth. The universe is a small, local phenomenon inside a mathematical reality that extends without limit in every direction. Bekenstein died on August 16, 2015, in Helsinki of a heart attack. He was 68. He died 1 month before LIGO detected gravitational waves for the first time, a detection that validated the general relativistic framework that his own work on black hole thermodynamics had helped to deepen. He never knew he was one of the most important physicists of the 20th century, and he died before seeing the confirmation of the world his equations described. The mathematics knew. The mathematics always knew. The gravitational waves were there in 1916, encoded in Einstein's equations. The Higgs boson was there in 1964, encoded in the gauge symmetry. The positron was there in 1928, encoded in Dirac's equation. The mathematics did not wait for the experiments. The experiments waited for the mathematics, and the mathematics extends far, far beyond what any experiment could ever reach. I want to stop here and address something directly, because I think There is a version of what I have been saying that sounds like philosophy, and another version that sounds like physics, and the difference matters. The philosophical version is this: mathematical objects seem to exist independently of the physical world. Plato said this 2,400 years ago. Godel believed it. Penrose argues for it. Tegmark takes it to its logical extreme. Interesting, perhaps, but abstract. Something for academic conferences and late-night conversations. The physics version is this: the Bekenstein bound is a derived result in general relativity and quantum mechanics. It is not speculative. It is not controversial. It is a consequence of the same physics that predicts gravitational waves, which we have detected, and Hawking radiation, which follows from the same thermodynamic framework. The Bekenstein bound says there is a maximum amount of information that can exist in any finite region of space. That maximum depends on the energy and radius of the region and nothing else. And Graham's number, which is a specific, well-defined mathematical object with provable properties, exceeds that maximum for any region up to and including the entire observable universe. This is not philosophy. This is a conflict between two branches of established science. Mathematics says Graham's number has precise properties. Physics says those properties cannot be verified by any physical system. Both branches are rigorously established. Both are supported by extensive evidence. And they are, in a specific and non-trivial sense, incompatible with the assumption that mathematics is merely a description of physical reality. Because if mathematics is merely a description of physical reality, then there should be no mathematical objects that exceed the descriptive capacity of physical reality. But there are infinitely many of them, and they have been there all along. The reason you were never told this is not that the physics community is hiding something. It is that the physics community has a culture, a professional norm, an unwritten social contract about what kinds of questions are considered appropriate. Asking, why does math work, is considered philosophy. Asking, what is the ontological status of mathematical objects, is considered philosophy. Asking, does Graham's number exist, is considered philosophy. And philosophy, in the culture of professional physics, is something you do on your own time, not something you publish papers about if you want tenure. But the evidence does not care about professional norms. The evidence keeps accumulating, and the implication keeps getting harder to avoid. Let me make it concrete. You are, at this moment, a physical system. Your brain contains approximately 86 billion neurons, connected by roughly 100 trillion synapses. Electrical signals are propagating through those synapses right now. As you process these words, the chemistry of your brain is governed by quantum mechanics. The forces holding your atoms together are governed by the standard model of particle physics. The gravity keeping you on your chair is governed by general relativity. Every aspect of your physical existence is described with extraordinary precision by mathematical equations. Now ask yourself this: if you are entirely described by mathematics, what is the you that is separate from the mathematics? What is left over? What is the non-mathematical residue that makes you a physical being rather than a mathematical structure? The standard answer is matter. You are made of atoms, of quarks and electrons, of stuff. But what is an electron? It is a quantum of the electron field. What is a quantum of the electron field? It is a specific excitation pattern described by a mathematical function called a quantum field. Its mass is a number. Its charge is a number. Its spin is a number. Its interactions are mathematical operations. Its evolution in time is governed by a mathematical equation. When you strip away every name and label and look at what physics actually says an electron is, what you find is a mathematical object. The same is true at every scale. An atom is a solution to the Schrödinger equation for a particular potential. A molecule is a quantum mechanical system with specific eigenstates. A cell is a thermodynamic system governed by statistical mechanics. A brain is a network whose dynamics are described by differential equations. At no point in the chain from quantum fields to consciousness does anything non-mathematical enter the picture. At no point does physics say, and now, in addition to the mathematics, there is also stuff. There is only the mathematics. I do not know how to make that sentence less uncomfortable. I have tried. I have spent a long time sitting with this and looking for the exit, the place where you can say, but the math is describing something, and that something is what is real. But the describing something argument has a problem, and the problem is Graham's number. Because if the math is just a description, then the math should be limited by the thing it describes, and it is not. The math extends infinitely beyond the physical universe. The math contains objects that the universe cannot even represent, let alone instantiate. If math is a description, it is a description of something that does not exist. And if the something does not exist, then the description is the only thing that does. This is not a new argument. Godel made it in the 1940s. Penrose made it in 1989. Tegmark made it in 2007. But there is a reason it has not penetrated public consciousness. And the reason is not that the argument is weak. The reason is that the argument, if correct, changes what you are. You were taught that you are a physical being in a physical universe, that your consciousness is produced by your brain, which is made of atoms, which are made of quarks, which are fundamental, that the mathematical laws of physics describe your universe from outside, the way a map describes a territory. The argument that Graham's number, Ramsey theorems, the Bekenstein bound, and the unreasonable effectiveness of mathematics collectively make is different. The argument is that the mathematical structure does not describe the territory. The mathematical structure is the territory, and you are not a physical being who uses mathematics. You are a pattern in the mathematical structure, a pattern that happens to have the property of experiencing itself as physical. The experience of physicality, the sensation of touching things, of occupying space, of moving through time, is what a certain kind of mathematical pattern feels like from the inside. And the mathematical structure that contains you extends in every direction, far beyond anything you can see, touch, compute, or comprehend. Graham's number is in there. Tree of 3 is in there. The Busy Beaver values are in there, even the ones that are provably inaccessible to any system within the structure. Rayo's number is in there, whatever it is. And structures so vast that we lack even the vocabulary to name them are in there too. You live in a small, quiet, computable corner of something that has no edge. I want to return to the people now, because this story started with people, and it should end with them. Frank Ramsey, who died at 26 in a London hospital after a surgery that may not have been necessary, proved that mathematical structure compels order into existence. He did not know he was doing this. He was trying to prove a lemma, But the lemma turned out to be a window into the architecture of mathematical reality, a proof that sufficiently large structures have no choice but to contain certain patterns. The structure does not ask permission. The patterns are there because the mathematics demands it. Ronald Graham, the juggler, the trampolinist, the man who did backflips in supermarket parking lots to pay for graduate school, calculated a number so large that it exceeds the information capacity of the physical universe. He did this not as a stunt, but as a genuine upper bound for a genuine problem, and the number he found has outlived him and will outlive every physical object in the cosmos. The number is permanent. The universe is not. Kurt Godel, who starved to death in Princeton because he could not trust the world to be what it appeared to be, proved that mathematical truth is larger than any system that tries to contain it, including, presumably, the system that contains you. Jacob Bekenstein, who died of a heart attack in Helsinki 1 month before LIGO confirmed the physics he spent his career developing, calculated the limit of what the physical universe can hold. The limit is real. The limit is finite. And mathematics, the thing that appears to contain the physical universe, does not respect that limit. Eugene Wigner, who called the correspondence between mathematics and physics a gift we neither understand nor deserve, asked the question in 1960 and received no answer. Not because the answer is unknown, because the answer is known, and it is too uncomfortable to say in polite, scientific company. These are not marginal figures. These are not fringe theorists. These are Nobel laureates, Fields Medal winners, presidents of mathematical societies, chief scientists of major research laboratories, and the question they were all circling, from different directions and in different decades, is the same question. Is mathematics something we invented? Or is mathematics something we are inside of? The evidence, 6 decades of it, points in one direction, and that direction is the one this story has been building towards since the opening sentence. There is an objection I want to address before going further, because it is the objection that every working physicist reaches for first, and it is the one that seems most reasonable on the surface. The objection is this. Of course, mathematics extends beyond the physical universe. Mathematics is a formal system. You can write down any axioms you want and derive any consequences you want. Graham's number is just a consequence of certain axioms. It does not exist in any meaningful sense. It is a theorem, not a thing. This is the formalist position, and it was the dominant view in the philosophy of mathematics for most of the 20th century, largely because of David Hilbert, who proposed in the 1920s that mathematics is nothing more than the manipulation of symbols according to rules, and that questions about whether mathematical objects really exist are meaningless. Godel destroyed Hilbert's program in 1931, but the formalist instinct survived because it is psychologically comfortable. If math is just symbol manipulation, then there is no mystery about why it works. It works because we designed the symbols and the rules to match the physical world. End of story. No metaphysical anxiety required. But the formalist position has a problem, and the problem is truth. Consider the Goldbach conjecture. Every even integer greater than 2 is the sum of 2 primes. This has been verified computationally for every even number up to 4 times 10 to the 18th power. It has never been proved. It has never been disproved. And the formalist says, if we cannot prove it within our formal system, the question of whether it is true is meaningless. There is no fact of the matter. There is only provability. But the Busy Beaver function tells us otherwise. There exists a specific Turing machine with approximately 27 states whose halting behavior is equivalent to the truth of the Goldbach conjecture. The machine either halts or it does not. There is no third option. The machine's behavior is a physical fact about a well-defined computational process, and if the machine does not halt, then the Goldbach conjecture is true, regardless of whether any formal system can prove it. The truth is there, sitting in the behavior of a finite state machine, whether or not any axiom system can reach it. Godel saw this with perfect clarity. He wrote in a 1964 essay that the incompleteness theorems show that mathematics cannot be identified with any formal system. The content of mathematics exceeds the reach of formalization. And if the content exceeds the formalization, then the content is the primary reality, and the formal system is merely a partial window onto it. This is the point where most people want to stop and say, fine, math is very interesting, but what does this have to do with me? Everything. Because you are a mathematical system. Not metaphorically. Your brain is a dynamical system governed by differential equations. Your body is a thermodynamic system governed by statistical mechanics. Your DNA is an information processing system governed by molecular biology, which is chemistry, which is quantum mechanics, which is mathematics. There is no level of description at which you stop being mathematical and start being something else. You are mathematics all the way down, and the mathematical structure that describes you is a tiny, local, computable fragment of a structure that extends without limit into regions of incomprehensible complexity. The computable numbers, the numbers that could in principle be calculated by any algorithm, are a vanishingly small subset of the real numbers. The real numbers are a vanishingly small fragment of the mathematical structures that exist in set theory. The structures accessible to Zermelo-Fraenkel's set theory are a vanishingly small fragment of the mathematical structures that exist in principle. You live in a corner, a warm, well-lit, computable corner where the numbers are small and the structures are finite and the physics is well behaved. But the corner is not the room is not the building, and the building extends in directions that the corner cannot see. I want to make this visceral because the abstraction can make it feel safe, and it is not safe. Right now, as you listen to this, the Ramsey numbers that Frank Ramsey proved must exist are sitting in the mathematical structure, determined, fixed, permanent. R of 5,5 has a value right now. It has always had that value. It had that value before the earth formed. It will have that value after the sun burns out. Whether any human being ever computes it is irrelevant to its existence. The mathematics does not need you. Right now, the last 500 digits of Graham's number are what they are. They were fixed before anyone calculated them. They were fixed before Ronald Graham was born. They were fixed before the universe existed. If the phrase, "before the universe existed," even makes sense in this context, which, if Tegmark is right, it does not, because the universe did not precede the mathematics. The mathematics preceded the universe. Right now, the Busy Beaver function has a definite value for every input. BB of 6 has a value. BB of 1,000 has a value. BB of 1,000,000,000,000 has a value. Most of these values are provably inaccessible from within any consistent formal system that models the physics of this universe. They are true, but unknowable. They exist, but cannot be reached. They are features of the mathematical landscape that the physical universe is too small, too simple, too computationally weak to detect. And somewhere in that landscape, there is a mathematical structure that describes you, a structure that encodes the position and momentum of every particle in your body, the quantum state of every field in your vicinity, the entanglement relationships between your atoms and every atom they have ever interacted with. That structure has properties. It exists in the same mathematical reality as Graham's number and tree of 3 and the Busy Beaver values. And it is, in the same sense that they are, permanent. The Bekenstein bound says you cannot hold Graham's number, but the mathematical structure that contains Graham's number holds you. And that is not a metaphor. I want to tell you about one more number because it brings the story full circle. In 2014, the year Tegmark published Our Mathematical Universe, and the year the upper bound on Graham's original problem was dramatically reduced, a team at the Planck satellite mission released their final measurements of the cosmic microwave background radiation. The data confirmed that the observable universe is flat to within a margin of 0.4%. A flat universe, in the context of general relativity, has a specific mathematical property. It can be infinite in extent. If the universe is spatially infinite, then it contains infinite copies of every possible configuration of matter, including infinite copies of you having this exact experience at this exact moment, an infinite number of times across an infinite expanse of space. This is not speculation. This is a direct consequence of the inflationary model combined with the measured flatness of the universe. Max Tegmark himself derived this in a 2003 paper in Scientific American. But here is what I find unsettling about that calculation. The number of possible configurations of matter in a region the size of the observable universe is bounded by the Bekenstein bound at roughly 2 to the 10 to the 122nd power. That is the number of distinguishable quantum states the observable universe can occupy. It is an enormous number, but it is finite, and in an infinite universe, every finite configuration repeats. Your exact configuration, every atom in exactly the position it occupies right now, every photon, every neutrino, every gravitational wave passing through you, must recur at an average distance of roughly 10 to the 10 to the 122nd power meters away. That distance is incomprehensibly large, but it is not Graham's number large. It is not even close. In the hierarchy of large numbers we have been discussing, the number of meters to your nearest identical copy is essentially 0. It does not even register on the scale that starts with Graham's number and escalates through tree and Busy Beaver and Rayo. The physical universe, even if it is infinite, is small compared to the mathematical landscape. Infinite repetition of finite patterns is still simpler, still more constrained, still more local than the mathematical structures that exist in Ramsey theory alone. An infinite physical universe repeating the same 10 to the 122nd power configurations forever is, from the perspective of mathematics, doing the same boring thing over and over. The mathematical landscape is not repetitive. It does not cycle. It does not plateau. It escalates through levels of complexity that transcend computability, transcend formal systems, transcend any mechanism the physical universe has for accessing them. The physical universe, infinite or not, is a thin film on the surface of mathematical reality, and you are a pattern in that film. And the patterns in the film have one property that the patterns in the deeper structure do not. The patterns in the film experience things. They have consciousness. They ask questions. They build particle accelerators and telescopes and write equations on blackboards. They produce Frank Ramsey's and Ronald Graham's and Kurt Godel's and Jacob Bekenstein's, people who spent their finite lives reaching briefly toward the infinite structure that contains them. None of them reached it. That is not a failure. The mathematics guarantees that no finite system can reach it. It is a structural feature of where you are and what you are. You are a computable pattern in a landscape that extends beyond computability. You are a finite structure in a reality that extends beyond finitude. You are a knowable system in a framework that contains unknowable truths. And the framework does not care about any of this. The Ramsey numbers are what they are. The Busy Beaver values are what they are. Graham's number is what it is. The mathematics does not need you to exist in order to be true, but you need the mathematics in order to exist at all. I want to sit with that asymmetry for a moment, because it is easy to read it and move on, and moving on would be a mistake. The relationship between you and the mathematical structure you inhabit is not the relationship between a person and a house. A person can leave a house. A person exists independently of the house. The relationship is closer to the relationship between a wave and the ocean. The wave does not exist independently of the ocean. The wave is a pattern in the ocean. Take away the ocean, and the wave does not find somewhere else to be. The wave simply is not. You are a pattern. The mathematical structure is the medium. If the structure were different, if the equations of quantum mechanics had different coefficients, if the constants of nature took different values, if the mathematical relationships that define the electron and the proton and the photon were altered, you would not exist in a different form. You would not exist. The mathematics that defines you is not a description of you that could in principle be separated from the you it describes. The mathematics is you. The rest, the sensation of solidity, the feeling of time passing, the experience of consciousness is what the mathematics feels like from the inside. And the inside is small. The inside is a sliver. The inside is one computable corner of a landscape that contains objects so vast that the entire physical history of the universe, from the Big Bang to the heat death, is not sufficient to even enumerate their digits. You live in a structure that contains you the way the ocean contains a single ripple. The ripple is real. The ripple has properties. The ripple experiences things. If a ripple could experience things. But the ripple is not the ocean. The ripple is not even a significant fraction of the ocean. The ripple is a local perturbation that the ocean does not notice. Graham's number is part of the ocean. You are the ripple. There is a misconception I need to correct before we reach the end, because I have seen it repeated in every popular account of Graham's number I have ever read, and getting it wrong obscures the real point. The claim you will find everywhere is that Graham's number is the largest number ever used in mathematics. This was true in 1980 when the Guinness Book of World Records said it. It has not been true for decades. Tree of Three, which appeared in a genuine mathematical proof by Harvey Friedman, is incomprehensibly larger. SSCG of 3, which appeared in another genuine proof by Friedman, is larger still. Specific Busy Beaver values, which appear in published results about computability, are larger than all of these. Graham's number held the Guinness record for a few years. It has not held any meaningful record since the 1980s. The second misconception is more dangerous. The popular version of the Bekenstein bound claim is that thinking about Graham's number would cause your brain to collapse into a black hole. This is not what the physics says. The Bekenstein bound is a limit on information storage density, not on thinking. Your brain does not need to store every digit of Graham's number in order to think about the number. You are thinking about it right now, and your head is intact. What you cannot do is represent the full decimal expansion of Graham's number in any physical system, including your brain, because the information required exceeds the maximum information density that physics permits for any region of space with a mass energy of a brain. The distinction matters because the real claim is more disturbing than the pop version. The pop version is about brains. The real version is about space-time. The Bekenstein bound does not single out brains. It applies to every physical system. A computer the size of the sun cannot store Graham's number. A computer the size of the observable universe, running since the Big Bang, using every quantum of energy available, encoding one digit per Planck area of its boundary, falls short by a margin that the computer itself cannot compute. The limitation is not biological, it is physical. It is a property of space-time itself. Mathematics has produced objects that space-time cannot contain, and this creates a genuine philosophical emergency that the academic community has been navigating around for decades. If you are a materialist, you believe that everything that exists is physical. Mathematical objects are not physical. Therefore, mathematical objects do not exist. But Graham's number has determinate properties. Its last digit is 7. That is either true or it is not. If it is true, something makes it true. What? Not a physical fact, because the number cannot be physically instantiated. Not a formal derivation, because formalism says truth is identical to provability, and there are truths about the number that exceed any particular formal system. Something makes the last digit of Graham's number is 7, a true statement, and that something is not in the physical universe. If you are a formalist, you believe that mathematical statements are true only relative to a formal system. But Godel showed that any sufficiently powerful formal system contains true statements it cannot prove. So there are truths about mathematical objects that are not relative to any formal system. They are absolutely true. Where does that absolute truth live? If you are a constructivist, you believe that mathematical objects exist only insofar as they can be constructed. But the Busy Beaver function has definite values that cannot be constructed by any algorithm. BB of a trillion has a specific value that no Turing machine running on any physical hardware for any amount of time can compute. If constructability is required for existence, then BB of a trillion does not exist. But it does have a value. The value is there. No one can reach it, but it is there. Each of these positions has the same problem. The mathematics is too big. The mathematics extends beyond what materialists can accept as physical, beyond what formalists can access through proof, beyond what constructivists can reach through computation. And the mathematics has properties anyway. The position that remains, the one that has no internal contradiction, the one that accounts for all the evidence, is the one that makes everyone uncomfortable. Mathematics is not a tool. Mathematics is not a language. Mathematics is not a game with symbols. Mathematics is the thing, the base layer, the substrate, and everything else, matter, energy, space-time, consciousness, you is a local pattern in that substrate. Graham's number is not large. You are small. The universe is small. The difference between Graham's number and the information capacity of the observable universe is not a statement about Graham's number. It is a statement about the observable universe. The universe is a tiny, finite, computationally limited structure embedded in a mathematical reality, with no boundary, no ceiling, and no obligation to be comprehensible. That is not the version of reality you were taught in school. That is not the version of reality that the popular science ecosystem delivers. That is not the version of reality that most physicists will say out loud at a conference, because saying it out loud gets you classified as a philosopher, and in physics, that is not a compliment. But it is the version that the evidence supports, and the evidence has been accumulating since 1931, when a 25-year-old Austrian logician proved that mathematical truth is larger than any system that tries to contain it, and it has not stopped accumulating since. I want to end where we began, with a number, and with what the number means about you. In 1971, Ronald Graham and Bruce Rothschild published a proof about edge colorings of hypercubes. The proof required an upper bound. The upper bound turned out to be a number so large that it exceeded the information capacity of the observable universe. A number so large that the number of its digits exceeded the information capacity of the observable universe. A number so large that the recursion of the number of digits continued for more layers than any physical process could track. In 1977, Martin Gardner told the public about this number. In 1980, the Guinness Book of World Records enshrined it as the largest number ever used in a mathematical proof. And then the world moved on. It filed Graham's number under interesting fact and went back to assuming that mathematics is a human invention, a useful tool, a language we speak because it helps us build bridges and launch rockets. Nobody told you what the number actually means. Nobody told you that the number exists in a mathematical structure that the physical universe is too small to contain. Nobody told you that we can prove exact, deterministic facts about this number, despite the impossibility of any physical system representing it. Nobody told you that the field of mathematics that produced this number, Ramsey theory, proves that order is not a feature of the universe, but a command issued by mathematical reality to the universe. A command the universe has no capacity to refuse. Nobody told you that the Bekenstein bound, one of the most firmly established results in theoretical physics, places a hard limit on how much information the physical universe can contain, and that mathematical reality exceeds that limit by a margin that the limit itself cannot express. Nobody told you that the man who invented Ramsey theory died at 26 from a surgery that a 2023 medical paper suggests may not have been necessary. Nobody told you that the man who computed Graham's number juggled 6 balls and did backflips into his 60s, and married a mathematician and kept a bedroom in his house for Paul Erdos, and died in 2000, having created an object more permanent than anything the physical universe will ever produce. Nobody told you that the man who calculated the information limit of space-time died 1 month before gravitational waves were detected, never knowing that the physics his work helped build had been confirmed. Nobody told you that the man who proved mathematical truth exceeds any formal system starved to death in Princeton at 65 pounds, because he could not trust the world to be what it appeared to be. Nobody told you any of this, not because it is secret. Every fact in this story is published, peer-reviewed, and publicly available. The 1960 paper by Wigner, the 1931 theorems by Godel, the 1981 bound by Bekenstein, the 2014 hypothesis by Tegmark, the 2023 breakthrough by Campos, Griffiths, Morris, and Sahasrabudhe, the 2024 determination of BB of 5, all of it sitting in the open literature, available to anyone, read by almost no one outside the relevant academic departments. The reason you were never told is the same reason the physics community does not talk about the implications of the Bekenstein bound in combination with Graham's number. It is the same reason Tegmark's hypothesis is treated as eccentric rather than urgent. It is the same reason Wigner's 1960 paper is admired as elegant and then shelved. The implication is too large. The implication rearranges the furniture of your entire model of what reality is. And people, including physicists, including mathematicians, including the entire apparatus of science communication, prefer to leave the furniture where it is. But the furniture was never where you thought it was. The physical universe, this one, the one with your body in it, with the stars and the galaxies and the cosmic microwave background radiation, is not the container. It is not the room. It is not the building. It is a pattern, a specific, local, finite, computable pattern in a mathematical structure that has no boundary, no ceiling, and no floor. Graham's number is in that structure. Tree of 3 is in that structure. Every Busy Beaver value, including the ones that are provably inaccessible from within any consistent formal system, is in that structure. Rayo's number, if it is well defined, is in that structure, and structures so large that no notation yet invented can name them are in that structure. The structure does not stop. It does not have a largest element. It does not plateau. It escalates through levels of complexity that transcend computation, that transcend formal proof, that transcend every mechanism the physical universe has for accessing them. And you are in that structure too. Not as a visitor, not as an observer, as a pattern, a finite pattern in an infinite landscape, a pattern that happens to have the remarkable property of experiencing itself, of asking questions about its own nature, of building telescopes and particle accelerators and writing theorems about numbers it can never contain. A pattern that, right now, in this moment, is confronting the possibility that the structure it inhabits is larger than anything it can see, and that the part it cannot see is not empty. The mathematics did not start when humans started counting. It does not end when humans stop. It was there before the Big Bang, if before means anything when you are talking about mathematical truth, which exists outside of time entirely. And it will be there after the last proton decays, after the last black hole evaporates, after the physical universe, if it is finite, reaches thermal equilibrium and nothing moves and nothing happens and nothing changes. The Ramsey numbers will still be what they are. Graham's number will still end in 7. The Busy Beaver values will still be determinate. The mathematical structure will still contain patterns, proofs, theorems, truths that no mind in the physical universe ever accessed. Ronald Graham built a number more permanent than the sun. Frank Ramsey proved a theorem more permanent than the earth. Kurt Godel demonstrated that mathematical truth is more permanent than the universe, and Jacob Bekenstein showed that the universe knows its own limits, even if the things inside it do not. You were taught that mathematics is a tool you use, a language you speak, a game you play. You were taught that the physical world is the real world, and that numbers are abstractions, convenient fictions, bookkeeping. That is the version you were given. And it is the version that Graham's number, by existing, by having properties, by sitting in a mathematical landscape that dwarfs the physical universe, the way the physical universe dwarfs a hydrogen atom, quietly, definitively refutes. The number does not need the universe. The universe needs the number. And the number is still there, right now, in a structure you cannot see, with properties you cannot verify, in a landscape you cannot reach. It was there when Frank Ramsey died at 26. It was there when Ronald Graham did his last backflip. It was there before the first star ignited. And it will be there after the last one goes dark. And you, all of you, every atom and every thought and every memory and every moment of your entire existence are a rounding error in the margin between 0 and its smallest digit. That is not a comforting thought. It was never supposed to be. It is a true one. And the people who know it is true have known for a very long time. They just never told you.